If an electron in a hydrogen atom jumps from third orbit to second orbit, it emits a photon of wavelength lambda. What will be the corresponding wavelength of the photon when it jumps from the fourth to third orbit? The Rydberg formula relates the wavelength lambda of emitted photons to the initial and final energy levels Ni and Nf in a hydrogen atom, and it is written as 1 by lambda equals R into 1 by Nf square minus 1 by Ni square, where R is the Rydberg constant, Ni is initial energy level, and Nf is the final energy level. For the transition from third to the second orbit, wavelength is calculated as 1 by lambda equals R into 1 by 2 square minus 1 by 3 square, which equals R into 1 by 4 minus 1 by 9, which equals R into 9 minus 4 by 36, which equals R into 5 by 36. Thus, lambda is equal to 36 by 5R. For the transition from fourth to the third orbit, wavelength is calculated as 1 by lambda dash equals R into 1 by 3 square minus 1 by 4 square equals R into 1 by 9 minus 1 by 16 equals R into 7 by 144. Therefore, lambda dash equals 144 by 7R. Let us now find the ratio lambda dash by lambda, which is equal to 144 by 7R divided by 36 by 5R, which equals 144 by 7 into 5 by 36 equals 20 by 7. Thus, the corresponding wavelength of the photon will be 20 by 7 lambda. Therefore, the correct answer is option A.